machen wir es. And, okay, so I just start right away. And as you can see, I have a very short agenda, more or less. So we start, of course, let's just change the pointer. So, of course, we will have a short introduction. We already in the beginning talked about what is a digital twin. So that's you can talk about that for hours. We don't do that, but just a bit of what we think a digital twin is and some technologies and use cases in the context of Industry 4.0 and challenges of digital twins and conclusion for future work. And that's from the perspective, I'm educated electrical engineer and did my PhD in mechanical engineering. And one of the other things, I'm a computer scientist. So I try to work very interdisciplinary and had the honor to have one of the books published together with my dear colleague Manuel Wimmer. And that's why it's a pleasure to be here. As said, we have 4 different research areas in my team, the model-based development part, and you always see some of the plants and the projects we do on the bottom of this slide. We have the intelligent production systems, where I used to lead the agent working group of the German national membership organization of IFAC since more or less 10 years. We do, of course, smart data, as all of us do, and human-machine interaction. And what we will see today is all the 3 parts anyway, so I don't have to do more. Well, we all know this figure at least until the 4th industrial revolution, and some of us think it's already time for the 5th industrial revolution. And what we at TUM, at the KI Fabrik, Bavaria, summarize is we focus on human-centered production and resource efficiency. And that's where all the talk will be framed by saying, okay, we want to have a human-machine interaction which follows these rules. Okay, so the hypothesis for the talk today is model-driven engineering is necessary for traceability and maintenance. Decomposability of structure and function improves reuse, and evolvability and learning during operation is mandatory. So, of course, this is not more or less self-evident, but I hope we will, after the talk, have a better impression about what is helpful in which part and what is necessary to do and reach it. Well, let's start with the digital twin as such and better understand what are the differences. So, of course, since long, we have digital models, and that's not very new. That's around for years. We have digital object and physical objects, but there is no automatic data exchange in between both. And then there was a paradigm of digital shadows, and that was introduced already in the frame of cyber physical production systems. We more or less have a digital shadow, seeing we have a physical object, and the digital object is somehow the shadow of this physical object. So you can only see in your shadow what is physically instrumented with sensors and actuators. So only these parts are available, and you don't have an automatic data flow, as you can see. And the digital twin, more or less, is where we want to have both connected all the time. Many of us still, if they say digital twin, even in the EDTR, the German working group of the VDMA, think more or less like digital models. So they think, okay, a digital twin is just a simulation of the model. We don't think so of the simulation of the physical object. We think it's more. And we will hopefully, after the talk, have an agreement on that point. Well, let's have 2 definitions. The one is the resource perspective, a dynamic virtual representation of a physical object or system across its life cycle, using real-time data to enable understanding, learning, and reasoning. And the second one is the industry perspective. As we have realized it, a digital twin refers to a virtual representation of a physical asset or system throughout its life cycle. So it's very similar. So both are virtual representation and throughout the life cycle. Nevertheless, if you look for all the different definitions, it's more around. And you can, I know from the GMA working group on digital twins, they really struggle with providing a smooth and precise definition. Well, looking at our plant, we started in the very early Industry 4.0 version, having a network with different, this is Germany, different facilities. I need to be very quickly now, because we will see later on, we have one point here when the bottle is coming through this part, we need to have a look at these filling, because we need it later on. So now we will see how the balls go through these pipes into this bottle, and we will later on realize that this is a critical issue if it comes to, can this plant produce different type of products? What will we need? We need the description of a plant, its capabilities, and its configuration. So in PPR, it's a resource, its capabilities or operations, the unit status like PECML, and the data points for tracking and tracing. And in the early days, we did that with plant agents, and all the different colleagues from Hamburg, with Alexander Fey to Stuttgart, with Peter Göhner to Aachen, with Sabina Jeschke in the old days, to Cottbus, Magdeburg, and Dresden, we agreed on having an agent-based concept where all the plants were mimicked by such an agent. Okay, so we all know if we want to have a new product, we might need a new technical process, which might need a new resource machine. I know that in computer science, a technical process sometimes is not included, but for us it's important because a technical process like forming or separating might be realized by different resources, which is more the implementation of a technical process. And we know these dependencies. If we have new machines, we can have new products, can have new processes. And of course, we have a lot of influences and constraints by legal authorities or energy efficiency or other issues. Okay, so our plant, you have seen it in the video, is hierarchically composed. And I guess some of you are not very familiar with ESA 88. That's why I'm explaining it. So we have this logical part with the robots, the barcode scanners, the switches, the conveyor belts, and we do have a filling part. And as you can see, we have two filling stations and one in between for preparation. So if we go now for ESA 88, the decomposability would look like that. We have the physical model saying, okay, from the enterprise to the control module with the different areas in between. And we have the procedural control model, meaning the process. So we have recipes to come up with our product. And we have the process model saying this is the process stages. So this is a control model. And so we could have also different operations on the different levels but it's not named operation. It's named phase, operation, unit procedure, and recipe procedure. And these realizes the different process parts. And you see very small up here that the entire filling process can be subdivided into different substeps. And if we now recall the name of skills and capabilities, that's very close to capabilities. But ESA 88 is very, very old. So it was long before the skills concept has been very prominent. Well, now we go to what I promised. If you look at these silos and we look at the different balls, we can, if there is a request, for example, somebody likes a specific fruit like pineapple, then we need to decide, we had never produced yogurt with pineapple, can we do pineapple? Or to make it easier, can we have black and white chocolate balls or maybe even strawberry chocolate balls? And what you can see immediately, this is an automation ML description, so it's exactly hierarchical. We would need to know, do our new balls pass these pipes to make it very easy? And therefore, we would need to have an automation ML, CIX, structural description, and we would need also the geometry, and we would need, okay, the input diameter is about, the output diameter is about, and there you can see another output diameter. And once we want to double check, is the new yogurt with the new type of balls feasible, we would need to know at least it fits through these pipes. Of course, we would need to know more, and this is exactly here. So our agent representing these plants would need to know, well, there's a new product description which has white chocolate balls with a viscosity, a yield strength, a diameter, And is it feasible to produce it? Therefore, we need the resource description. And then we need to have the ontology as knowledge base and double check, can all the product description details be produced on our resource, and then very easily mimicked here. We say, okay, the viscosity is processable by the system, the diameter fits through these small pipes, and the yield strength is also acceptable. So for our request from the product agent, we can say, okay, we can produce these specific strawberry balls or pineapple balls. Lovely. And that's for adaptability. So now, of course, that would be also included in the digital twin. But we have another issue. So the second question is, who can produce this little bottle through the entire system? And as you can see, in the old days, when it started with Industry 4.0, we realized such an agent-based platform, having a customer agent configuring his or her yogurt, having a service agent, and all the different facilities with the different chairs in the early days, and later on also for a fair. It was the Automatica 2014 with an agent management system, knowing who is available, knowing which services these plants can deliver. And we had a message transportation system, which was programmed right from scratch. And it was nothing with OPC-UA, because OPC-UA was not there at that time. And as you can see, we have a lot of these type of questions. So who can transport me? So digital twin of the bottle asks, I need to pass here and there, and who can transport me and who can produce me. So it could be an exchange in between the bottle product agent and the different bells and the different switches here. So that's what we realized. As said, it's 2014. Of course, I don't want to be just with old material. So what we think how systems should be built nowadays, we have these digital twin for our self-adaptable manufacturing systems. We have the capabilities of the different parts of a machine or even of different machines, and they provide their information model for MES systems or others. And what you can see here, they include automation ML descriptions, and also E-class or MTP or any other description which is available for these from the design, from the engineering period. And of course, we know the devices included, and we know the skills which are available in these different machines. Please be aware the skill definition is also quite different if we look for robotics or automation or production, 3 different skill definitions. So on the base level, on the field level, we have this multi-agent systems, and they are able to execute these skills and therefore make it happen and change if necessary. So from our point of view, if we go for evolvable digital twins, we do have on the one hand the design period. So we have the mechanical simulation, for example, we have a product requirements, we have electrical, a CID, we have the software part, meaning the functions like a state diagram. We do have the automation control code. And then we go for industrial engineering, so preparation to build the mechanics and the electricals. The electrical part, therefore, we do have production resource planning and MTM. So you may not know MTM. This is a method how we can design human working places. It's basically very easy. Dividing, decomposing any action into different sub-actions. Then we have also very popular human models like Ramses or others, where we know the sizes of the people and how long they can reach. And we have virtual commissioning. Up to now, at least from the best of our knowledge, this integration of the human is still a weak spot. On the other hand, so we have, as said, model-driven engineering. For these, we have decomposable model-driven engineering. And now this is a digital twin as built, meaning that was when we deliver it to wherever, and that's when we, as a machine and plant manufacturer, it leaves our premises. Then we go to the operation part here in this blue. So we have a lot of production actuators and sensor signals we need to take into account. We have product quality data. We have machine and plant downtime. We might have key performance indicators of the machines. And there might be even mixed reality and some teleoperation in this part. And what we think is we need both in this cycle. So to improve the digital twin and the plant of the next generation, we need all this information. That's why we summarize learning during operation. Gathering data during operation will help to improve the next generation of machines. Of course, there are some specific models like DEXP, for example, which is important for process industry. Okay, just summarizing, I think you all know it. The Industry 4.0 terminology, we all know RAMI, which is exactly mentioned here. And in the old days, when 1980 to 2000, we always had this automation pyramid, meaning we have very many operational tasks on the lower level, getting less on the upper level, but many dispositive tasks on the upper level and very few on the lower level of this pyramid. And we strictly separated the different bus systems for the field, meaning the dirty environment, and for, let's say, the control level and the more like upper levels like MES or ERP system. Then the Diabolo was presented by ESA, and we figured out, okay, these two levels are not anymore separated. They somehow are just one level, but therefore we need the information model. And there's still the interface to the MES. And the interface in this information model, we have some of it now in the reference architecture of Industry 4.0 and also in the OPC-UA. And what you can see here from the RAMI model, the old automation pyramid is in this level. And what has been added, you may know that, is a life cycle and value stream. This was exactly the definition we introduced some slides ago, and also the business areas, which is quite tricky sometimes for the one or the other company. And of course, the reaction speed on the lower level is much higher, but therefore the data volume is much higher on the top level. So that's where we are. And of course, if you look now for the asset administration shell, which is quite, I would say, German speaking, of course, Austria is also very much involved. What do we think? We have an asset, might be even an old plant, so a brownfield plant, and we want to connect it to Industry 4.0, then we need an administration shell. And the administration shell allows to provide all the digital information. And now you can guess we are talking about digital twins. So for us, in the administration shell, we do have our digital twin and the knowledge of our agents. And as said, we are here in this, not only in the design and the maintenance part, and on all the different levels. Okay, so looking for the internal structure, everybody might know the asset administration shell, so it's just a short wrap-up. Of course, we have this identification, and we have the submodels, which include the technical properties like material weight and the operational data, and also the quality inspection data. So that's what we expect if we say asset administration shell. And of course, also the CID data. So it's just another representation of the circle of we need all included, the design and the operation part. Well, and of course, for us, it's the XML standard, automation ML. It can be then transferred to the asset administration shell. And of course, we include also ontologies to do these decisions. Can the product be produced on this resource? Are the capabilities there? And is this process step feasible on this type of production plant? Well, just one example where you also can use ontologies. This is a project together with colleagues from the product development part and colleagues from the gear production. So we set up a gear ontology to be better able to discuss with the different domains how we can solve a problem. So for example, you see classically a top-down approach, and then it's about a form fit of a drive and a gear. And then you can see, okay, what type of parameters are available for the different motors, for the different gears. and then you can automatically decide how it works. So unfortunately, some German words still in here. So if we have these semantic digital twins available as an ontology, we can check whether the shaft and the hub are fitting to each other or not. So for us, it was interesting to say, okay, we do have different opportunities to solve a problem. So a very mechanical issue, how can I connect, let's say, a shaft with a gear? And here you see one of these connection points. And we have, in principle, several opportunities. And as you can see, we do have different drives. And we wanted to do that in a very early stage to figure out which solutions are not to be later on discussed anymore in detail engineering. And what you can see here, these green parts are still available. The red and the yellow one, it's like a traffic light, are not longer necessary. So the width of the keyway must be the same for shaft and hub, very easy. The depth of the keyway must be suitable for shaft-hub combination. Length of a keyway of shaft must be smaller than keyway of hub. Shape of the keyway must be the same. So that's for German Passfeder-Nut-Verbindung. So maybe it's easier for the one or the other. So that's a typical solution. How can we connect two mechanical parts? And it was very hard to include also information like characteristics and fields of characteristic into the ontology and the SysML model. So that's what we have done. And we are proud of this, but it's still not finished. It's still ongoing. And some of you may not know E-Class. So especially if you are in Asia, nobody knows E-Class, but we are not in Asia, we're in Austria, so you may know. Otherwise, it's UNSPIC, which is not that powerful. So if you want to describe a specific part, in this case, we want to describe a cylinder, and we want to change it, then we need to know all the E-Class details, for example. And what you can see here, E-Class Advanced gives us a lot of detailed information also on motion profiles. And here, as said, it's not just that we need one sensor. We really need to consider motion profiles or even environments in specific areas, which allow us to select only a few different motors and no other. That's what we are doing here, trying to include all the necessary information from E-Class Automation ML to find the appropriate device and using the digital twin to do that. So once again, that's what you have seen. We just put in the middle Automation ML, and E-Class would be also such a means to do so and to find the different views. And of course, there's not only CIX, we also have PLC Open or the behavioral modeling in XML, and of course also the Collada, meaning the geometry. So of course we are also doing such things in the AI Factory or KI Fabrik Bavaria, and there we have cooperation partners Wittgenstein and BMW, and they have provided us with challenging use cases. And what we should do here with the digital twin, we create it during engineering and we refine it during operation to enable the exchange of such SS-related data. And it's not very visible, but you can imagine for BMW, it's about how can we put this part with its cable and using robots mounting and fixing these cables also in different shapes for different type of BMW cars. And also from Wittgenstein, how can we assemble such a motor using also a lot of small pieces? And if you're a mechanical person, you know that's not so easy to mount and to fix these parts. And it should be done by, as said, having different skills and different capabilities. So in the AI Factor, we have a so-called brain, which is a central AI and production as a service. Then we have our agents, which of course on the one hand can do the transportation to the right working stations, and we have the kindergarten, meaning where our robots learn what they can do. And of course we have a collective learning, you see here mimicked, but it's really there. We have some very nice robots which in parallel try to learn what is feasible and what is the best approach. And that's situated in the Deutsches Museum, which is a quite lovely place, but not allowed to visit now. We are still trying to improve. And it's there are many researchers in robotics included, and we fully use such a product as a service approach, seeing modeled in sequential, not as in sequential function charts. Sorry, not sequential function charts. That's IC 61131. You see sequence diagrams from UML and SysML. So saying, okay, we have the different agents and they can communicate with each other. Are they capable to do so? If yes, then they start and so forth. And the question is this real time, and what do you need to do to make it real time capable? That's still undergoing from our publication. So we have the capabilities with their descriptions. And of course, this is done by different researchers because every unit is described and operated from a different research group. Well, what are the challenges remaining? What we have seen already is this type of concept, which is not very, I would say new, but the challenging thing is how can we do this in reusable hardware functions and also software functions? Therefore, we introduce control primitives saying, okay, and now we are in a world which is a bit strange for classical computer scientists. This is IC 61131, which is lovely runnable on so-called programmable logical controllers, which are necessary to fulfill the dependability and security functions. So we have this capability definition with pre and post conditions. That's classical OCL, if you wish. And of course, we have parameters to do so. And then we have now, that's a sequential function chart, how this can be executed. This is a skill definition. And what is new, this has been around for some time, but always the fault handling and diagnosis was neglected. And this is the charming part in this approach by Jan Wilch. We are now able to, who is a PhD in my group, to build in such fault handling. And I hope that will be a game changer, because in this case, it's much more composable, because up to now, it's very tricky to get these functions which don't include faults recombined, because that's most of the engineer, more than about 50%. So then we have the skill instances. As you can see, we know what can the control primitive do. And if there is a fault, it can still recover. And at the moment, we are working together with colleagues from Chalmers to improve it also to higher level of the automation pyramid. So we propose a decomposable structure, but including fault handling and diagnosis. And how is that done? So it has been, of course, developed by having a lot of surveys with many companies, by guidelines. We have now a PLC Open guideline, which has been published thanks to Eva Maria Neumann. We have code analysis, and therefore we know all these metrics. We can use existing code and analyze it. And from this knowledge, we came up with the new call pattern control primitive, saying, okay, we do have to include this extra functional aspects like diagnosis and communication in the part of the software itself. And therefore, we need a bit of a different, we need some kind of state machine where we do have the different operation modi, and we need to map it to the hardware, and we need to know how it is to be implemented. Okay, let's have a look whether the film is starting. I shortly have to change. So what you can see here. Okay, this is our very small plant where it's operated, and of course we will insert very soon a fault. The moment everything is running smoothly. Of course, it's a very simple one, just sorting work pieces from one area to the other. And of course we can interrupt it now, and then we can see whether it works properly or not. So I hope it's soon having the problem. But you can see on the one hand, this is the IC, and these are the variants we do have of these different devices. Unfortunately, it doesn't seem to be included. If we can show that if we have an interrupt here, we can still operate any further. So Now we don't have the fault included, which is a bit of a bad situation. Sorry for that. If we have problems also to change, for example, the crane's situation or the linear motor of the crane, then, and we see we need another version which has more, another speed level and different velocity, then we can do that by including the E-class ID and referencing to the external file, which is nothing new, which just can be done. And what we realized by having seen, and I try once again whether I'm lucky with these different, it's a bit of a noise, but I think you can see here are faults. I'm not sure whether you have seen it. It's not exactly in the middle. So you see this is not positioned correctly, and we can see it also on the other one. Let's double check here. So if these are faults we have not seen during, let's say, the design, but you can see very simple processes don't work because there are some faults in gripping. So what we have done after having a properly designed plant with this crane, we have also in the simulation, we included the swivel time, and we tried to simulate it, but everything worked fine. Then we really run these experiments some months ago, and we saw these type of faults. And we came up why and when do the faults occur, and this is just a small summary. You can see we do have, especially if we have a heavyweight workpiece, we have a lot of problems. Here you see 100% of all cases we have a problem when a specific PLC cycle time is set. If we do have this heavy workpiece and we have a very short PLC cycle times, it sometimes works. And so also depending in the blue one, always it works fine if we have, let's say, a very low crane velocity. So depending on the crane velocity and the weight, this fails. And this is something which has not been included in the, or not seen in this during a simulation, because we were not aware that the or let's say the simulation guy was not aware that the PLC cycle time is a critical issue. So normally a very experienced person would know, but as said, we are not always very experienced person. So what we wanted to show very hands-on is if we go for design of a very simple system, it still is important to take into consideration that very simple faults occur. So summarizing it, we don't need to see the video once again. We have seen that this learning during operation has been shown pragmatically by these cranes movement. And so summarizing what we have learned, normally it's absolutely quite clear for us. Simulation alone is not enough. We need to have a holistic view on the whole product lifecycle. Especially, we need to learn from the operation part. We need to have a comprehensive monitoring and control, meaning we have to have a very nice software architecture concept. We need to come up with a fault recovery and maintenance in our production systems. And we want, of course, to predict and optimize the behavior. So knowing can we have it faster, knowing can we operate specific products, meaning on the one hand, the velocity of the crane, on the other hand, the product like a new fruit in our yogurt. And therefore, we need test beds for such new processes and technologies. And just one short figure, I'm not sure whether everybody is aware of it. So this is a classical, say, V model-like situation. We have normally a system specification, we have a basic design. And in our world, it's not only the software design, but also the mechanical and the electrical. And normally, the mechanical starts earlier. Then we have this detailed design and also cabinet construction. And of course, we do have construction of and manufacturing of the mechanical parts. Then, of course, we go for system integration. This is known. But then it comes to the issue that we might operate this plant up to 50 years, which is not a joke, which is the result of a survey of the German Association of Electrical Companies, like Siemens and others, ZVOE. And they figured out that, yes, 50 years might be a very good number of operating of plants. And you can imagine that it needs some update and retrofit. So if we want to operate a plant for 50 years, we might need an electrical retrofit all 7 to 20 years. And we might need a software update all 1.5 years approximately. And then, of course, we do have new requirement specification. At the moment, there is a real issue that we don't have any information for older plants. So we have some research projects trying to figure out and automatically derive digital twins from old documentation where only PDF documents are available. So how can we assure that old plants still can be assigned to a digital twin? And how can we do that long after the plants have been built and are operating since years? So that's what I wanted to tell you today. So as said, my group is working in the engineering operation and also knowledge operation. Thanks for your attendance, and I'm ready for questions.